Hello everyone, my name is Akash. I am a second year PhD student at Oxford University at the Photovoltaics and Optoelectronics Devices group. This video today is going to be about a paper me and my co-author Suhas have recently released, and we hope this is going to be the first of many in this series coming out of our research group. We think that making videos like this will make the research that we do more accessible to people and also present it in a more easy to digest way for the researchers. This is the very first one we're doing, so it might be a bit rough around the edges, but we hope you will stick around and forgive some of the flaws. So in this paper, released in ACS Energy Letters only about a month ago, we look at using this imaging technique in order to take macroscopic pictures of perovskite solar cells. Perovskite solar cells, which is what we work on for those who do not know, are a type of solar cell that has been showing some really promising performance in the last decade. However, despite all of this progress, the highest efficiency solar cells tend to be extremely small, no bigger than a fingernail, not really something you can put on your roof and reliably get power out of. One of the things that stops us from making them much bigger is the fact that a lot of these films that we form are very inhomogeneous. And so an important part in making these things upscalable is going to be understanding the homogeneity of these materials that we're depositing. A good way to assess how homogeneous something is just taking a picture of it, imaging. And this is what we've done. We do something called luminescence imaging. That is, we shine some light on a sample and we take a picture of the glow that comes off of it. This is something that has been used in silicon solar cells for a long time in order to make spatially resolved maps of series resistance, for example. And we wanted to then apply something similar to perovskites to see what kind of features we would observe. The setup we used can be seen here. It's relatively simple. We just have our sample with a camera in front of it with a filter in order to image the photoluminescence and a blue light in order to excite the sample. If the sample is a fully built solar cell, we can actually even electrically contact it by connecting it to the source meter. This gives us a picture of the photoluminescence, and actually we can get images of something called the photoluminescence quantum efficiency, or PLQE, using some cool white referencing that we describe fully in the paper. This is good because the PLQE is a thing that can be used to work out a lot of different parameters. For example, the quasi-Fermi level splitting, which is very closely linked to voltage, or ideality factor, which is a parameter from the diode equation. By making a map of the PLQE, we can basically make maps of all these other parameters and then see how homogeneous they are across our devices. Just taking a map of quasi-Fermi level splitting, which is something that's really closely linked to voltage, for example, we can see that in our cells there are millimeter scale heterogeneities. That is to say that the voltage that the solar cell is producing is not homogeneous across its surface, and we can see that in these images. These features are at the scale of a millimeter, so it's at the scale of the device. They're really very large and are likely to be the first thing that we would need to optimize out when we are trying to come up with recipes that make nice and smooth solar cells. So the idea is, by taking these images, we can see which recipes and deposition processes cause more homogeneous films and focus on optimizing those in order to make our cells more upscalable. Something we really did want to look at also was the photoluminescence at short circuit. See, when you have a solar cell and you connect it in short circuit, that is, you connect the leads together, you should have zero photoluminescence. This is because photoluminescence comes from electron-hole pairs generated in your solar cells recombining and releasing some light. Except at short circuit, all the charge that you've generated should be extracted and there should be nothing left to undergo photoluminescence. Having said this, however, in perovskite solar cells, people have observed a very large amount of photoluminescence, and a lot of people have linked this to a current loss, which makes sense. Any charge that's generated but not extracted is a loss in your current. So this is something we wanted to investigate in a spatially resolved way to see if we can, just like the previous map which tells us how smoothly our voltage is distributed, if we could see whether this current loss was something that had inhomogeneities in it. The parameter that we are mapping is something we're calling the charge collection quality, which is on the screen here and we derive in the paper. In order to calculate it, you need three measurements: a measurement at open circuit, a measurement at short circuit, and a map of the ideality factor. All three of these are measurable using our setup, and so by making a map of this charge collection quality, we can make a map of current loss. In order to verify that the charge collection quality is a useful metric to use, we measured the average charge collection quality and the short circuit current for a variety of different devices that are made here in our labs. These were across different band gaps and across different device architectures. We were not able to measure the ideality factor for every single data point, and this is because it's a longer measurement which requires an intensity dependent measurement, so we weren't able to measure them for a lot of these data points. What we did was we plotted the charge collection quality using only the open and short circuit images, assuming the ideality factor was uniformly 1. Then we plotted this against the short circuit current that we measured, and we've drawn some bands here about where we would expect these points to be if the ideality factor was varying between 1 and 2. As you can see, all the data points fall really nicely within this expected band, which gives us a lot of confidence about using this parameter as a proxy for current loss. Making a spatially resolved map of this parameter for the same cells I showed you earlier, then we can see that even in this current loss there is very similar macroscopic millimeter scale heterogeneity. In fact, for certain samples, like the second one, the quasi-Fermi level splitting was fairly smooth, meaning that the voltage was fairly regular across the device. But in terms of the current, we can see points of low collection quality which indicate low current extraction. So taking both these pictures together gives us a much more holistic image, pardon the pun, about the performance of our devices. We then also investigated specifically which layer in our device stack would be adding more inhomogeneity. We did this by measuring the quasi-Fermi level splitting of half stacks. These are devices with only one transport layer and the perovskite layer. We found generally that bottom contacting layers, that is layers that the perovskite grows on top of, had introduced less inhomogeneity with respect to perovskite on glass than the top contacting layers. And we believe this is because the perovskite is able to grow on top of these transport layers, which adds some benefits in terms of uniformity. We looked at some of the commonly used transport layers and ranked them in our paper according to how much inhomogeneity they add. Here the size of the bubbles is indicative of how much inhomogeneity it added to the perovskite, for example. So that's basically all the data from the paper. The important points were that we showed that this charge collection quality was a good metric for current loss, showed in macroscopic millimeter scale inhomogeneities in this current loss, and we demonstrated how we can find out exactly which layer is adding inhomogeneities in any specific device stack. We hope that other groups will be able to implement this into their workflow. We used relatively simple off-the-shelf components, and it didn't require very much expertise to set up. So we hope that this is something people can start using more regularly as a step in optimizing their devices. That's the end of the video. We hope this was okay. This is again the very first one we're doing, so might have some rough corners, but hopefully this was helpful to our fellow researchers. We hope this has provided a nice and more digestible way compared to reading a whole paper in order to kind of keep up with the research that we're doing. Well, thank you, goodbye, and yeah, thanks for watching.